Gravitational force. It has been well known since ancient times, and we're talking about ancient Greece, way before Columbus, that Earth is a sphere, and objects that are near the surface tend to fall down. Newton connected the idea that objects, like apples, here's an apple over here, fall towards the center of the Earth with the idea that the moon orbits around the Earth. But he said it's also falling towards the center of the Earth. That's the point that people didn't get. The moon's motion is approximately that of uniform circular motion, with its velocity perpendicular to its centripetal acceleration. So here's the velocity, here's the centripetal acceleration. Gravity provides the centripetal force, just like gravity allows an apple to fall down. Now, why doesn't the moon fall to the Earth like the apple? That was Newton's genius, and that will be explained when we examine the International Space Station. Newton concluded that all objects attract one another with a gravitational force. The magnitude of the gravitational force decreases as the centers of the masses, and that's in bold, that's very, very important, increase in distance. So we have two cases. Here we have the distance between the centers of mass, or r, and here it's 2r. There's more gravitational attraction here. The magnitude of the gravitational force decreases with the inverse of the square of the distance between the centers of two masses, is proportional to each of the two masses, and also is proportional to a constant g, the universal gravitational constant. So we have these two masses. They're being attracted by each other. They're at a distance r, and note once again the distance r is measured between their centers. The two forces are equal. That's Newton's third law, right? And that's equal to g times the mass of one times the mass of the other divided by r squared. The direction of the force is along the line connecting the centers of the two masses. Each mass feels a force of attraction towards the other mass along that line. So there's the line connecting them. Here's the force on this object due to this object, and here's the force on this object due to the first object. And a way of saying that in vector form is F12, and that's a vector, got the arrow on top of it, equals the negative of F21. That shows they're the same magnitude but pointed in opposite directions. Newton's third law tells us that the forces acting on the two masses are of equal size in opposite directions. That means that if I drop a pen, the force of Earth pulling the pen down is equal to the force of the pen pulling the Earth up. However, since the mass of Earth is so much larger, that force causes the pen to accelerate down, while the movement of Earth up is completely unmeasurable. Newton's law enjoyed a great success when it was used to predict the existence of Neptune based on motions of Uranus. So they were predicting a planet here that they hadn't seen based on a planet that was observed. Mathematical calculations were conducted by John Adams and Urbain Le Verrier to explain discrepancies in Uranus's orbit based on the laws of Newton and Kepler. Le Verrier sent coordinates of the new planet to Berlin Observatory astronomer Johann Galle, who confirmed the existence of the planet on September 23, 1846. Neptune was discovered. In 1798, Henry Cavendish measured g, the universal gravitational constant in Newton's equation. He did not initially set out to measure g. He was trying to measure the density of the Earth. By measuring g, however, he had weighed the Earth and other planets, since their masses could then be calculated, as we'll soon see. Example 1. What is the magnitude of the gravitational force acting on a 1 kilogram object, which is 1 meter from another 1 kilogram object? Answer on the next slide. We list our givens. We have one mass, second mass, and the distance between the centers of the object. That's what we'll assume if they don't tell us any different. And here's the universal gravitational constant found by Henry Cavendish. Newton's equation, gmm over r squared. Here's the constant, here's the two masses, and here's the distance between them. Now, fortunately, all those numbers are 1. So our answer will be the force is 6.67 times 10 to the minus 11th newtons. Very, very small. Example 2. Two spherical objects have masses 2.5 times 10 to the 5th kilogram, 3.4 times 10 to the 3rd kilogram. The attraction between them, gravitational attraction, is 5.4 times 10 to the minus 5th newtons. How far apart are their centers? We start by writing down our givens. We have our masses, we have the force, and we want to find the distance between the two objects. And here's the universal gravitational constant. We start with our equation, but we need to solve that for r. Remember, always solve for the quantity you're looking for before you plug any numbers in. So we multiply both sides by r squared, then we divide both sides by f, and we come up with this equation for the distance between the two spheres. So please proceed to the next slide. We start with our equation, and you can see why these things get fairly long because of the exponents and such. We have g, and then we have our two masses, and then we have the distance, and we take the square root of it all. So there's a lot going on here, so take a minute, check where each number came from, then proceed to the next page. This can be typed directly into a scientific calculator. But it would be easy to make an error, right? You've got the exponents here to worry about, you're dividing, you have a square root, whole lot of activity. A safer approach, and this is the old school approach when you just had slide rules and no calculators, is to regroup all the coefficients, powers of 10, and units and calculate them separately. Check to see how that was done below. Okay, so you know what? I'm going to erase this stuff up here. And here's 6.67, there's a coefficient. Here's a 2.5. Here's a 3.4. And in the bottom we have a 5.4. Then we take our exponents, 10 to the minus 11th, and we have 10 to the 5th, 10 to the 3rd, divided by 10 to the minus 5th. That's this piece here. And then we put all our units together. So again, please pause the video and see what we did and move on when you're ready. So under the radical sign, step 1, calculate the new coefficients. So that's 6.67 times 2.5 times 3.4 divided by 5.4, and we get 10.5. That was pretty straightforward. 2, calculate the new power of 10 by adding exponents in the numerator and subtracting those in the denominator. So we have minus 11 plus 5 plus 3 minus a minus 5. And that then gives us plus 2. Then do the indicated math on the units. That's over here. So what are we canceling out here? We have kilograms canceling out with kilograms squared. We have newtons canceling out with newtons. And we wind up with meters squared under the radical. So you put those together, we have 10.5 times 10 squared meters squared. Take the square root, you get 32 meters. That's the distance between the objects. Example 3. Two spherical objects have equal masses and experience a gravitational force of 2.5 times 10 to the minus 9 newtons towards one another. Their centers are 0.50 meters apart. Determine each of their masses. We start with our givens. We have a force, we have a distance between them, and then what do we say about the masses? They didn't give us the masses of them, did they? And we have to find each of their masses, but they tell us they're equal. So what we can do is say m1 is equal to m2, and then since they're the same, we'll replace both of them with m. So here's our equation, Newton's equation. First thing we do is we replace m1, m2 by m squared. Then we multiply both sides by r squared, and we're still trying to find m. So then we divide both sides by g, switch the left to the right on the equation and the right to the left, and we get m squared is fr squared over big G. Take the square root of both sides, and here's the mass, and that will be the mass of each object. Now, finally, I substitute the numbers in, and you can either use a calculator or the method we showed you on the previous slide and find out that the mass of each one of these objects is 3.1 kilograms.